Hi, the time is 5 past 5. Good afternoon, everybody. Today's lesson is not going to be that long because we had a long lesson yesterday. So I know people want to rest and it's actually later in the afternoon. Right. Today I posted a lesson on Google Classroom and it was about global air circulation. Right, so yesterday I spoke roughly about global air circulation and what it entails. So today we're gonna talk about what's happening there and what you guys are gonna be doing and just to make you understand the content. Right, if you look at your ATP, it says global air circulation, world pressure belts, and tricellular circulation. So today we're going to look at global air circulation and tricellular circulation. Okay, so on your screens now, you can see that it says grade 11, lesson 4, and then the energy balance for the whole Earth. Right, so the energy balance of the whole Earth depends on how the ocean currents are moving and how the wind is blowing. Right, I think everybody understands when we talk about ocean currents, we're talking about the direction in which the water is flowing in the ocean in regards to how the wind is blowing. Remember, ocean currents cannot be created if there is no wind. Okay, so the movement of the wind and the water around the world is the one that determines the energy that is transferred around the world. So the wind will carry a warm and a cold breeze, and then the oceans will carry a warm and a cold current. Okay, hence we have the distribution of energy across the whole world. Right, if you look at the picture on your screens now, it's figure 2.10, the energy balance for the whole Earth. All right,
There's
so
no picture.
you can't see it.
Yes, sir.
Let me see. Let me see. Okay, what can you see now? Can you see anything now?
No, sir.
All right. How about now?
No, sir. Oh, yes, sir.
Yes, sir.
Yes, sir.
You can see
Yes.
it figure 2.10.
Yes.
Yes.
We can see.
Okay, so you
Mm.
the time that I was speaking, you heard what I said, but you didn't see what I was showing.
Can you please repeat, sir?
Okay, all right, all right. So I say, can you see that picture now?
Yes, sir.
Right,
Yes, sir.
the energy balance for the whole Earth again. The energy balance, the balance between incoming solar radiation and outgoing radiation from the Earth. Okay, so what I was saying is the distribution of energy across the world is determined by the ocean currents, and it's also determined by the breeze that is blowing from the North Pole, the equator, and the South Pole again. So this means that ocean currents can only happen if the wind is blowing again. So if the wind is blowing, it also carries warm a warm breeze and a cold breeze again, because remember it's coming from the equator or the North Pole again, the equator or the South or North Pole again. So this means that the air which is blown from the North Pole to the equator will determine the balance of energy there, né? And then also we have the water that is carried in the oceans across each and every part of the world also carries certain temperatures that determine how a place is gonna have its temperature again. So what I'm saying is the energy balance for the whole Earth is determined by the wind and the oceans. Okay, and then when we look at incoming solar radiation and outgoing radiation from the Earth, incoming solar radiation is when we have uh, rays from the sun that are radiated from the sun that come to Earth, and then they are trapped. Oh, what the hell did I do? Okay, they are trapped. So incoming is when the sun is shining. Like if you look at this part here, incoming radiation. So the sun is shining with this white arrow, which is the direct heat, which is 100% from the sun again. And then when it hits the Earth's surface, it becomes incoming solar for the sun, and radiation is the way it's coming in. So we call it insolation. Okay. So insolation is the one that is responsible for all the energy that is transferred to Earth from the sun. Okay. Now, when we have 100% of the sun coming into Earth, some of it goes into the water, some of it goes onto the land. Let's start with this arrow here. So this process of this energy from the sun going onto Earth is called radiation. Again, the Earth will absorb this energy through radiation. Again, and then this arrow bouncing off the Earth will be our terrestrial radiation. Once the Earth has accumulated the heat from the sun through insolation, it can also give it off to the atmosphere through terrestrial radiation. Okay, so the atmosphere is warm. Okay, so this part where we have the heat heating the oceans, this part might be where we have the equator, and then most of the highest temperatures are recorded there. And this water will flow as it flows across the world. It's also distributing heat through ocean currents. Okay, and then we have water vapor, and then we have uh, the atmospheric gases. They also accumulate heat, again, which is trapped in the atmosphere, and then the wind will blow across the world, and then the energy is also transferred through uh, the wind. Okay, right. Can you see the new page that I just put?
No.
If you can't see, yeah,
Okay, now we can, yeah.
so you can see. All right. So the unicellular model of global circulation. Okay. So these notes, I got them from the book because I couldn't let you guys write everything from the book, so I had to summarize them. Yeah? Right. This is one of the ways in which we're going to be discussing how energy is transferred across the world. Again, we said through ocean currents and through the wind. So the first one is going to be the wind again. So in its simplest form, the global circulation of the atmosphere would transfer heat from low latitudes to high latitudes in two huge convection cells, one in each hemisphere. Figure 2.15 shows, as figure 2.15 shows, né? Because there is one cell of circulation in each hemisphere, this model is called the one cell model or unicellular model of global air circulation. Okay, in this model, warm air rises at the equator and moves towards the poles. At the poles, the air becomes colder and sinks. The cold air travels back to the equator, completing the convection system. Okay, so heat can be transferred through convection, conduction, radiation, and terrestrial radiation. Okay, right now, this is what I was talking about. Yeah? The equator records the highest temperatures on Earth, which means the temperatures will be indicated with this red color that you see. Can you see that?
Yes, sir.
All right. So the red will represent the high temperatures at the equator. And then as the air is pushed out of the equator, the reason why I'm saying it's pushed out of the equator, remember, warm air will rise. And in this case, it's rising. And then it is pushed towards the top, where it becomes cooler on its path further away from the equator to the North Pole. And then it sinks going down because it's now dense, going down, and then it comes to contact with Earth and finds its way back to the equator. The same thing is happening in the South Pole. The air rises and then it travels towards the South Pole, reaches the South Pole, sinks, and then goes back to the equator. So this is the unicellular uh, model of global air circulation. Okay, all right. I said you should draw this in your books then, so you should draw it neatly, and then when we get back to school next week, I'll check your books and then we'll see if you're doing the correct thing. But if you follow the notes, you should be fine. Right, now we have vertical and horizontal air movement, links between horizontal and vertical air movement, surface convergence, and ascending air. Right, upper divergence ascending air. Remember, we said it only rises if it's warm. So it's pushed up as it goes with its temperature. And then when it reaches the North Pole, it becomes cooler and then condenses, goes back to the equator, and then the cell is complete in the northern hemisphere. Okay. And then in the southern hemisphere, the same thing happens. The air goes as it okay, the air comes down and then becomes hotter, surface divergence, and then goes out, becomes cool, and then it completes the cell. Okay. All right. Then move on to the next one. Link between air pressure and altitude. All right.
So must we also draw this one?
Yes, you must draw this one, please. Just draw this one and then you write the notes that follow these ones underneath the picture. Okay. Right, if you look at the columns there, A, B, and C, they're different again because of altitude. Altitude is height above sea level. So if you see at point A, it's at a lower altitude and then there's high pressure. B is medium and then C is at a higher altitude and then there's low pressure. Okay, so that is the link between pressure and altitude. So which means the higher you go, the lower the pressure. The lower you go, the higher the pressure. Okay, so this column here represents the pressure according to the altitude. Okay, right, place A, which is at sea level, has a greater column of air on it, therefore it has a higher pressure. So which means place A has a higher pressure because it is at a lower altitude, hence the pressure from the sea, from the surface of the sea going up, the distance is higher, and then you have more pressure. Then place C, which is found in the interior, has a small column of air resting on it, therefore it has a low pressure. So, which means place C is at a higher altitude, and then there is lower pressure because it's sitting at 1,500 meters above sea level, which is higher. Okay. Right, the relationship between vertical air movement and pressure. When air rises above a surface, a pressure at the surface will be low. When air rises above a surface, pressure at the surface will be low. Okay. When air subsides over a surface, the pressure at the surface will be high. So it's just basically the same thing here that we just spoke about. More air at the surface, more pressure. Less air, less air, more pressure. More pressure, less height, more pressure. Okay, it's just opposite. Right. So those are the notes that I posted for you guys today. And then I'm just going to go back to the textbook so that you guys can see which page we're working on. All right. So in the textbook, we are here. Right. So in the textbook, everybody's got a textbook. We are on page 95. Okay, that's the thing that I asked you guys to draw. So if you can't see it clearly in the notes, you can actually see where I got it from. And they are the notes that are highlighted over there. And then this is the stuff that I just spoke about now. And then instead of you guys writing all this, I summarized it and I gave you in 2 points. Okay. And then world pressure patterns. This is what we just spoke about now. And then for tomorrow, I wanted us to discuss world pressure belts. I think we said tri-cellular model of global air circulation. Right. If we're talking about a tri-cellular model of global air circulation, we're talking about the 3 cells. Okay. I spoke about this yesterday as well. We've got the Hartley cell, which is found at the equator, distributing hot air. We've got the Ferrel cell, which is found next to the Hartley cell, either on north or south part of the hemispheres. And then we've got the polar cell, which is found at 180 degrees north and south of the world again. So the polar cell basically generates cold air, and then the Ferrel cell basically has warm and cold air, and then the Hartley cell has hot air. Okay, now if you look at the key here, it will show you the pressure belts, which are shown in color, blue for low pressure and green for high pressure belt. Okay, so that is your tri-cellular model of global air circulation. So in a test, they'll give you a picture like this, and then they'll ask you to label which one is the Hartley, the Ferrel, and the polar. And then you are supposed to label Hartley, Ferrel, and polar. And then you explain what happens in each cell. Okay, right. When it comes to explaining what happens in each cell, you are supposed to talk about what happens in each cell. So in this case, in the Hartley cell, hot air rises from the surface and cools, producing tall cumulonimbus clouds. So you're basically talking about how the hot air is going to rise from the equator, moving upwards to the North Pole or moving downwards to the South Pole until it eventually turns into cold air as it passes through the ferrule and eventually at the polar cell. Okay. Right, in your notes, tomorrow you also see that I spoke about the tri-cellular model of air circulation. So you're going to write about that, and then you're going to draw this beautiful picture here, the one that I just showed you now, this one. And then underneath it, you're going to label in the Hartley cell what happens. There's the explanation in the ferrule cell and in the polar cell. Okay, right. And then tomorrow, we're going to be talking about this. Okay, that picture shows the tri-cellular model of global circulation. And in this case, the arrows now have changed color. As you can see, the Hartley cell is at the equator, which means it carries mostly warm air. Hence, we have the red arrows. Air cools to temperature of surrounding air, instability, convectional rain. Okay, so usually when you have warm air rising, it will condense in the clouds, causing rain. Okay, and then as you can see, the cell is moving, the Hartley cell is moving up and down. As it moves up, we have more blue arrows are starting to appear because the temperature is becoming lower. And then we eventually have blue arrows there at the polar cell on top. So these points here on the sides of the cells can also be a definition of what's happening inside the cells. Okay. Right, that is the end of the lesson today. Right, so tomorrow we want to talk about, we want to do the corrections, and then we'll discuss about this tricellular model, and then we'll talk about the notes that I'll have posted on the day. All right.
Must we?
Unmute. Boy, Amanda, you can ask. I'm waiting.
So
Yes.
for all the different cells, we have to write everything, like that whole paragraph for each cell.
Each cell has 4 points.
Not those little paragraphs under the points.
Which was, let me put the textbook on. Which little paragraphs are you talking about? These ones.
Yeah.
Okay, so what you're
No,
gonna
so
do?
not the ones
These ones.
so where they're describing in detail.
Like,
Yeah.
so you are gonna write 1, 2, 3, 4. Then you skip a line, you put another heading in the ferrule cell. Then you write 5, 6, 7, 8. Skip a line, put a heading in the polar cell. 9, 10, 11, 12.
Okay.
Yes.
So
Yeah, bo.
you see on the second diagram of that of the cells, ne?
This one.
Yes, sir.
Okay.
Let's say you draw it like that in the exam. Will you get penalized for not labeling everything?
Actually, if you draw it like this, it shows that you understand what's going on, because you can't actually write all those 12 points with the time that you're given for the question. So I would advise you to draw it like this. And if you have your red and blue colors, you just indicate the arrows with the colors, and then you put these points. It's still okay.
Okay, sir.
It's easier to actually study this one than the points that I gave you.
Okay, sir.
All right. Anybody else before we end the lesson?
You can end the lesson, sir.
All right then. So I'll see you tomorrow. Thank you so much for joining.
Bye.
Yeah, please listen to my song, you know.
Yeah.
Nice to talk to you.
When I send the link when
Salty, go home.
yeah, go home.
Leave,
Bye.
leave.